Hello and welcome to the Crash Course. Today I'm starting your first chapter from PU2 syllabus in mathematics, which is relation and function. Yes, the chapter is very easy. That's why this is going to be very important to get those 2 marks in our KCET examination. So without wasting time, let's start our session right away. First thing first is your types of relations. Let's start with types of relations. What is that going to be? A relation R on set A is called as empty set or void relation. When you have, so first definition is very simple on the void relation, right? So whenever you have none of the element related to any of the other element in the given set, let's say I'm defining a relation on the set A, okay, then none of the element of set A is related to any other element of set A, then it will be called as null relation or void relation. Please check. Definition is given over here. We can see example of relation as well. So we have a set A 1 2 3 4. The elements are given as 1 2 3 4 and relation is defined like this. Check difference of the elements. Okay, so basically 1 2 1 3 1 4, you can take any combination, should be equal to 5. Now think about it. If you take any 2 numbers from the given set A, can you get difference to be 5? Because if you take the least number, which is 1, and maximum number, which is 4, maximum number is 4 and least number is 1, difference will be in this case 3. You cannot get a difference more than 3. Then how can this relation be having any element? So if you write a relation R, it will be having nothing in it. It will have none of the element in it. There will be no ordered pairs in the relation R. That's why it's called as empty or void relation. Is it clear? Very simple thing. Let's move on. Okay, now just opposite to this, we have universal relation. Means where every element which is given in the set will be related to each and every other element of the set. Okay, so relation R on the set A is called universal if each element of a set related to every element of the set A. Okay, so basically A cross A is a subset of A cross A. Alright, for example, you can take over here are the relation defined on the set 1 2 3 are the elements over here. What it says, A minus B mod is more than 0. You take any 2 combinations, 1 2 1 3 3 2 3 1. You can take any combination possible, and the difference if you take, you'll have 1 minus 3. So the answer is minus 2. What about mod? We also have mod over here. Apply mod to this. So the answer is 2. Is 2 more than 0? Yes. So you take any combination, thus given relation is always true. Means any combination, any ordered pair. What are these combinations called as? These combinations are called as ordered pairs. I know you have all learnt it. It's called as ordered pairs. Okay, we write this as A comma B. In this particular case, we'll write this as 1 comma 3. 1 comma 3 is your ordered pair, which will be the element of the relation, right? So this element of the relation, this ordered pair, will be true if you take any such combination possible. Okay, hence this given relation R is universal relation. Simple. Okay, clearly for all ordered pairs, simple, same thing is explained over here. Okay, next we can move on. The next over here onwards, our question starts from where you can expect the question directly. Okay, so yeah, these are important because they are asked sometimes, but not that the chances of these questions coming from the universal relation or from the empty is less. But from here onwards, from the reflexive onwards, the question is going to be coming for sure. Means one question on this concept will come, so you have to pay attention over here, bacha. Okay, please check. And to learn this relation, you have to start from identity relation. You have to start from identity relation. So what is identity relation? Very simple. When the element of a set should be related to itself. Repeat after me if you're watching this session. When the element of a set is related to itself, that type of relation is called as identity relation. That type of relation is called as identity relation. Okay. What is written over here? Itself only. So not only itself. The word is, it has to be just by itself. It cannot have, let's say if I have an element 1, I should have 1 comma 1. I cannot have 1 comma 2. Example you take over here, if I have a set A, elements are 1 2 3, means for this relation, identity relation, I should have 1 comma 1, I should have 2 comma 2 and 3 comma 3. I cannot have 1 comma 2 or 2 comma 1. No, because the statement is itself only. Okay, but in the case of reflexive relation, there's a difference. Means of course this will require that part 1 comma 1 2, 2 and 3, 3. These three ordered pair has to be there, of course. Apart from that, even if you have something else, for example, if you have 1, 2 or 2, 1, anything else also is there. You can have 3, 1 or you can have 2, 3. All this can come, okay? Means apart from the original pairs of identity, that is 1, 1, 2, 2, 3, 3. Apart from these three, other elements, other ordered pair are also welcome to be present over here, and those type of relation is called as reflexive. So the common difference between these two is very simple. And what is that? In this case, you must have only these combinations. Means only ARA should be there. In this case, only you have ARA. That is only ARA. I hope this is visible. If not, I'll write again. Yeah. Please pay attention. This is very important. So only ARA should be there in the case of identity relation, whereas in the case of reflexive, you can have ARA. Apart from this, if you have other ordered pair also, that's okay. But this should be there for all the elements. For all A belonging to the set A. For all the elements, okay? You cannot skip any of the elements. For example, I cannot write 1, 1 and 2, 2. If I write 1, 1, 2, 2 and skip 3, 3. If I write this as without 3, 3, then this will no longer be an example of reflexive. For it to be reflexive, we must write 3, 3 also. So for all the elements present in the set, you got to have the identity proven, and then only you can take other elements as the part of the the relation. Now 3, 3 must be there, and then you can take away, you can have other elements as well. So I hope you got the definition of both of these as well as the difference between them. Okay, let's carry on from here. Next is again a very important relation. The questions will come directly on this, which is symmetric relation. A relation R on a set A is called symmetric. So this symmetric and transitive are actually conditional relation. Means there's a if and then statement. So you have if statement. Excuse me. Yeah. So you have if statement. What is that? If ARB is true. What's the meaning of ARB? ARB bacha represents a set. Okay. Sorry, ordered pair. Forgive me, not a set. ARB represents a ordered pair. So the statement is very simple. If ARB is present, is part of relation R. If ARB is part of the relation R, then BRA should also be part of R. What is the meaning of BRA? The ordered pair B, A. If it means, the statement means that if in the given relation you have the ordered pair AB, then you must have the ordered pair BA as well. And if you have both cases true, it means the given relation is actually symmetric relation. I hope this is clear. Okay, let me give you example over here. Yes, check. The set is again A 1, 2, 3. If you have 1, 2, you should have 2, 1. If you have 1, 3, you should have 3, 1. If you have 2, 3, you should have 3, 2 as well. Okay, this is the example of a symmetric relation. Can we move on to the next one? Yes. Next is the last one, which is transitive relation. This is the case where students make mistake. So I have few points that I want to tell all of you. One point is written over here, that I'll come to that later. Right now, one thing I want to mention. If there is no way, if there is no way means there's no means, there's no possibilities, okay, there's no way to object for the transitivity. If there's no way to object the transitivity, it means the given relation is transitive. I'll repeat. If there is no way to object for the transitivity, means you cannot prove that it is not transitive. What it means is, basically a relation is given to you, you cannot prove that it is not transitive. It means it is going to be actually a transitive relation. That's one way. Secondly, this is one a very important statement because student gets stuck in this. Second one is this is a property. Second one is my trick, okay, and not my, like lot of many of you already use it. Try to look for even one set of numbers, because when you talk about transitive relation you talk about 3 numbers A, B, C. So this is also a conditional statement. I'll show you. So you have over here in the if condition. In the case of symmetric you had only one if condition. Over here you have 2 if conditions. So you have ARB should be there and BRC should be there. BRC is part of the relation R. Okay. Then the statement is, then the statement is ARC, right? Excuse me guys, just a second. Yeah. Then ARC should be part of R. If ARB is there, if BRC is there, then ARC should also be there. That's the definition of your transitive relation. Okay, so first thing I said was how to identify relation. If there is no way to object for transitivity, you cannot disprove that it is not a transitivity. Okay, transitive relation, then go ahead with the statement as relation is transitive. Second is, whenever you are looking for transitive relation, look for one set of values of ABC. So one value of A, one value of B, and one value of C. Look for one such value, one set of values of ABC where you can prove that it is not transitive. Because what happens now, your student keep coming to me and asking me that, sir, let's say I give you example in any particular case that it is not transitive. You keep coming back and asking me that, sir, but we have example over here. Let's say I tell you that at 1, 2, 3 a given relation R. Forget about everything right now. Listen to me once again. Please focus over here. 1 second. Okay, I'm giving example. If I say that at the values 1, 2, 3, A equal to 1, B equal to 2 and C equal to 3, the given relation is not transitive. Then you keep coming back to me and telling me, sir, I have a value of A where A at 2, B at 3 and C at, let's say, 4. So A is 2, B at 3 and C is 4, or any other value, A 100, B 2000, whatever it is, and like that. So for different value of ABC, the given relation is transitive. So bacha, please don't look for the values where it is transitive. Look for the value where it is not transitive. Okay, because even if it is not true for one such value, the given relation is not transitive. Okay, so please do not look for the values which is actually proving the transitivity. Look for where you can't prove the transitivity. Okay, so wherever it is not possible, try to look for those values, try to look for those type of numbers. Okay, so even if you can prove that it is not transitive for one set of values of ABC, it means the given relation is not transitive. And tell me which is easier to prove it is not transitive or transitive. Okay, so go for not transitive. Okay, so try this approach. Take a value of ABC and check for the transitive property. Got it? These are the 2 ways. Third one is over here. I'll come back to this now. Now let's say in a given example or question to you, they have said that AA relation R has A in it, also has BB in it. A and BB is present. In a given relation R, the ordered pair A and BB is present, and they are asking you check whether if AB is there. You don't check for transitivity. If you are having AA, BB and AB, it's always transitive. Check out over here, AA, you make this A with A, you get AB now. AB is present over here. If you have BB, check here, AB, if you match this with this ordered pair, check this out, AB with BB, again will get AB only. So if you have AA, BB and you are getting AB or BA, or BA, don't check. It is going to be always transitive. Always transitive. So I'm going to ask you all, the 3 methods that I've taught you to check this is going to be, first one is, if you cannot prove the transitivity, if you cannot prove that, it's going to be, if you can't create an objection, it means it's going to be always transitive, first case. If you can't object to the transitivity, it means always transitive. Second case, if A, try to take values of A, B, C such that the given relation becomes not transitive. So then you can say simply it is not transitive, of course. And third option is if you have the cases of A, B, B, and you're looking for A, B is over here present there. Let's say you have 1, 1, 2, 2, and then you have 1, 2. Don't check for transitivity. It's going to be always transitive. If you have 1, 1, 2, 2, and 1, 2, somebody is asking you, is it transitive? Answer is yes. Repeat after me. If you have 1, 1, 2, 2, and 1, 2, is it transitive? Yes, it is always transitive. Okay, got it. So if you have AA, BB, AB and BA, presence will always be transitive, sir. Okay, super. So this completes your understanding of transitive relations. It's very important because this is where students make mistake. For a different question statement given, you guys forget about how to prove or how to find this quickly. Okay, that's why the tricks given over here is very important. Next up is the combinations. So when you have all three true, when you have symmetric as well, when you have symmetric as well, when you have reflexive as well as transitive, if you have all three to true, it means the given relation becomes an equivalence relation. The relation which is all three is going to be called as equivalence relation. You all know that. Let's move on. Okay, now number of relations, again rarely asked. The chances of this being asked is less, but still concept is there. That's why we have to learn that as well. So number of relations, please check. Number of reflexive relation is given by 2 power n times of n minus 1, where n is the number of elements in the given set. Okay, this set's cardinal, let's say this set is A, right? Then n of A equals to n, then answer is given by, for reflexive, 2 power n times of n minus 1. For symmetric we have 2 power n times of n plus 1 by 2, and for transitive again we have 2 times power n m times of m minus 1 by 2. This is taken as m over here. If you take n, it will become n times of n minus 1 by 2. Okay, for number of relation for which is both, actually, sorry, reflexive and symmetric. Okay, not transitive, forgive me, my bad. It's for reflexive and symmetric, 2 power m times of m minus 1 by 2. Okay, I was in the zone of solving for equivalence, that's why the word transitive came out of my mind. Let's continue. We have some questions on this, some examples we're going to solve, and we'll move on to the next topic, which is types of functions. Okay, for the set A equals to 1, 2, 3, define a relation R on the set A as follows. A 1, 1, 2, 2, 3, 3, so reflexive, yes. How many ordered pairs to be added to R to make it smallest? What is smallest equivalence relation? Okay, so it's reflexive, yes. Is it symmetric? No. But if I add 3, 1, then it is symmetric, because 1, 3 and 3, 1, symmetric. Okay, do we need to add anything else? Do we need to check for transitivity? No, sir, because check here, A, B, B, C, C, this is A, B, this is A, C, and this is C, A. Yes or no? Check now. This is A, B, B, C, C, and we have A, C and CA. I told you guys, if you have A, B, B, and if you have AB or BA, don't check for transitivity. It's always transitive. Same case, you have A and CC, and you have AC and CA. It's always transitive. Don't have to check for that. Okay, so this is also there. It means you need to add only one ordered pair, which is 3, 1, to make the given relation equivalence. Hence answer is, they're asking you how many ordered pairs to be added. We have only one, which is 3, 1. That's your answer. Okay, once you add this, it becomes automatically symmetric, and answer is option A. I hope this is clear. Moving on the set n of all natural numbers, define the relation R by ARB if and only if GCD, greatest common divisor, GCD is same as HCF. Okay, all right, is 2, so HCF should be 2. For any ordered pair, it should be 2. So is it true? Reflexive, is it possible? No, not necessarily, because if you have, let's say I have a number 8, 8, because defined on real number, right? Now defined on n. N is a natural number. So 8 is a natural number. I can make an ordered pair 8, 8. Is this property ARA? So 8, 8 is true. It's reflexive. But is it following the relation? Please check. HCF of 8, 8 is 8 actually. HCF is 8. So this is not possible. Okay. So first one is gone. Look for symmetric. Symmetric is if and then condition. It means if you have ARB, it means if ARB has ABHCF is 2, then of course BAHCF has to be 2, right? Is also 2. If AB means, let's say 2 and 4 HCF is 2, then 4 and 2 HCF is what? 2 only, right? So ABHCF is 2 means BAHCF is 2, so BRA is also going to be present in the relation. So this is true. This is true. Let's look for the last one. Look for the last one. When you have transitive relation, right? We can take a lot of examples where we have, check this out. We can take let's say 4 2, sorry, not 4 2, 2 4 we can take, or 4 2 2 8 4 8. Nah, yeah, we can take 4 2 8. Let's take A as 4, B as 2 and C as 8. What I'm doing over here, I'm using the second method, taking any 3 values of ABC, and we will check for our what do you call, the property of a relation, okay, which is going to be GCD of 2. Check here, GCD 2, yes or no? Yes, GCD is 2 here. What about this GCD? What about these B and C? GCD is going to be again 2. HCF of 4 and 2 is 2, HCF of 2 and 8 is 2. Okay, now what about HCF of 4 and 8? So it makes an ordered pair 4, 8, right? And HCF of 4 and 8 is what? Is going to be 4. So is it possible? In AB, this is AB, right? In ARB, the HCF is 2. In BRC, the HCF is 2. But in ARC, HCF is 4. It is then not transitive. Okay, so we have only symmetric, option B. We have only symmetric, which is option B. Good question. Please check. Alright, so this is clear, guys. Moving on to next question, which is again on the property of equivalence relation. Please check for any 2 real numbers A and B. We define ARB if and only if they have given the relation as sin square A plus cos square B is 1. Okay, so check for first one, reflexive. Check this out. Of course, it's a property, right? Sin square A plus cos square A is always 1. The property is the entity number 1 in your grade 10 trigonometric identities. Okay, this is true. Okay, so reflexive, yes. Symmetric, of course, if you have sin square A plus cos square B equals to 1, okay, then I have to prove, this is the condition from where? From ARB. From ARB. Let's look for BRA now. Right, sin square A as 1 minus cos square A plus cos square B as 1 minus sin square B equals to 1. 1 plus 1 will become 2, bacha, and here minus cos square minus sin square you can take common. It will become cos square A plus sin square B equals to 1. Now move this side, 1 on this side and this bracket on over this side. Okay, so we get 2 minus 1. I'm moving this 1 over here. Okay, 2 minus 1 and this will become plus. So I get cos square A plus sin square B. 2 minus 1 is 1. Let's write sin first because of the property, because of the given relation actually. So sin square B will come first. Sin square B plus cos square A, which is nothing but representing your BRA. So you had ARB, sin square A plus cos square B, and now you have BRA, sin square B plus cos square A is also equal to 1. It means it is symmetric as well. It is symmetric as well. So we have proved 2 of them right now, reflexive and symmetric. Okay, let's move on to the next one, which is transitive relation. Let's move on to the transitive. So we have to go with ARB first. This will come out as, okay, sin square A plus cos square B equals to 1. Continue. BRC, so sin square B plus cos square C should be equal to 1. Add these. Okay, add these. You get sin square A as it is, and you have cos square b and sin square b. Add them together in the bracket, cos square b plus sin square b, and last we have what? Cos square c. So right here, cos square c equals to 1 plus 1 is 2. We all know cos square b plus sin square b is 1. Again, the same property, identity number 1 from grade 10. This will be going to be equal to 1. So we have sin square a plus 1 plus cos square c is 2. If you move this over here, you get 1. It means you're getting sin square a plus cos square c equals to 2 minus 1, which is how much? Simply 1. And this is nothing but your condition ARC, hence equivalence. Okay, now if you are thinking that, sir, how can we do all of this in 1 minute? Actually, this can be done. I have done all the steps so that if somebody is not able to understand any step in their mind itself, so actually you can see here, this is directly proven in your mind. Over here, this is no step question. Over here, do we need this? No, we just need to write this step. So we need to write this step and our job is done. Okay, so so far we have got only one step. Here we need to write maybe just not even this. We know that if you're adding these, no, so this question becomes only 2-step problem. Writing this and adding this, you get answer going to be all relation is true in equivalence. Okay, so even though I've written almost 7-8 steps over here, in your paper, in your exam, you don't have to write if this question comes with 7th step, because very simple, you can see over here, this can be done in your mind. Yes, all of you should agree with me. How can we do this in our mind? By practice. Okay, if you are practicing these questions enough number of times, of course this whole thing will come directly to you. Okay, next we can move on to next category. All right, let's start. Next is, as you all know, the last topic from this chapter is types of function, where we talk about 1, 1, on 2. So again, I'll take some time because I want to explain every bit of this very interesting chapter and very easy chapter, right? So again, one more question will come from this side, one question from that equivalence relation, and one question from types of function is mandatory. So this chapter has a weightage of 2 questions, so 2 marks. We have to get both. Why? This is the easy chapter. Okay, this is the easy marks that you have to get out. So in that 60 marks of your paper, close to 30 is easier. Let's say 25 is easier, and then the other 25 is medium, and then the last 15 is difficult. Okay, so 40, yeah, close to 25 and 10, or 25 and 20 and 15, you can think like that. So basically easier marks cannot be lost, okay, because the toppers are getting that easy marks for sure. So to compete with them, you have to make sure that all the easier marks has to be with you without fail, bacha. Okay, chaliye. Types of functions. First one, so we have 4 categories over here, very simple. 1, 1, not 1, 1 is many 1. Repeat. 1, 1, not 1, 1 is many 1. On 2, not on 2 is into. Okay, so we have 4. 1, 1, many 1, on 2, into. Okay, so I'll give more energy of mine on 1, 1 and on 2. The other one is basically opposite of that. Okay, means what is not 1, 1 is simply many 1. What is not on 2 is simply into. All right, a function f defined from a to b. What is the meaning of this? F a to b. What's the meaning of this? A means domain and b means codomain. Try understanding this. Wherever from here onwards you should get this symbol in front of you, you should always know A means domain, B means codomain, and yes, it is important, very important. Okay, chaliye. So it's called 1, 1 if you have for every distinct element in domain. What's the meaning of this, sir? If this is my domain A and this is my domain, sorry, codomain B, okay, you'll have elements, right? Let's call this to be 1, 2, 3, 4. Here we have A, B, C, D, E. Okay, so for every distinct element in my domain, I should have a distinct image in codomain. So 1 should be with A, 2 is with B, 3 is with D, and 4 is with C. Okay, so I have a distinct images of the element in the domain with the elements in the codomain. Okay, then this will be called as 1, 1. This will be called as 1, 1. If not, for example, Do we have many one? Yeah, we have many one. So let me show you over here for the many one. If it is A and it is B, and you have the element, for example, 1, 2, 3, 4, and A, B, C, D, E. Let's say 1 goes to, okay, A, and 2 also goes to A. Means for more than one element, basically for 2 and more elements, we have the same images. Please check here. If there exist at least 2 elements, distinct element in the set A whose images are same in B, then the given function is called as many one function. The given function is called as, excuse me, many one function. The opposite of 1 1. All right. Okay, this is the mapping part. This is how we do the mapping. Function is also, you know that, right? The second name of function is called as mappings. Mapping from where to where? From domain to codomain. Okay, chaliye. So this is clear. The mapping part is clear, sir. Next is going to be the algebraic approach. Algebraic approach is very, very simple. Very simple. If you have x1 equal to x2, x1 not equal to x2. First case is x1 not equal to x2. Then the f of x1 should also be not equal to f of x2. Check here. Are 1 and 2 equal, sir? Are 1 and 2 equal? No. 1 is different, right? 1 and 2 are different. So 1 image is A and 2 image is B. So 1 is not equal to 2. So f of 1, which is A, and f of 2, which is B, in this particular case, are also not equal. You can say that f of 1 is not equal to f of 2. Okay, 1 is not equal to 2, it means f of 1 also is not equal to f of 2. When you have this condition, it means the given function from the algebraic approach is not 1, sorry, is 1 1, is 1 1. Next is just the opposite. If you have the function f of x1 should be, or it is equal to f of x2, f of x1 is equals to f of x2, then this means that x1 has to be equal to x2. It means actually when you're trying to say that f of x1 is equal to f of x2, what it actually means is that the point x1 and x2 are the same. Okay, so basically it's the same thing. Okay, you don't have two different points to say that the function's values are different, okay, or equal. Alright, this is clear. When f of x1 is equal to f of x2, x1 and x2 has to be equal. When x1 and x2 are not equal, then f of x1 is also not equal to f of x2. Is it clear? Yeah. Chaliye. So this is the algebraic approach. Mapping is done. Now the last is the graphical approach for faster solving of the questions. Whenever you have a graph like this, straight line, or whenever you have a graph like this, exponential graph, okay, so whenever you have a graph like this and you do a horizontal line test and you get only one intersection, then the given function has to be 1 1, and every other case is going to be many one or not 1 1. For example, sir, mod of x, how many intersections? 2, so not 1 1. Got it? If I take a parabolic curve, again not 1 1. Getting my point, right? So I hope you understood both 1 1 and onto very clearly. So 1 1 and many one very clearly. This is 1 1, this is many one. With the mapping you understood, right? Next we want to move on to methods to check whether the function is 1 1 and onto or not. Sorry, 1 1 and many one or not. I already taught you that. Method number 1. Consider in two elements x1 and x2 belongs to the domain A. If f of x1 equals to f of x2, then simplify this equation. This should also be the case. Okay, already taught you this, bacha. Already taught you this. When I was explaining you all of this, no? Already explained you this part, the theory part over here. Methods to check the function of A to B is 1 1 or many one. This also I taught you. Parallel line to x-axis, the straight line, sorry, horizontal line test. Okay, if you have, excuse me, if you have one point intersection, means the function is 1 1, otherwise it is many one. Okay, so this is done. Next is your onto function. Okay, now onto function, you have to define the different ways to do it. Some are very complicated as well. Okay, we go ahead and find the range and everything, but simply one statement, one word does it. What is the set B? What is this? A to B. What we have learned? A is sir you said na A is domain, correct. What is B? B is codomain. But sir, you did not say anything about range. We have range, right? We have range as a set. We have learnt in PU1. If you know it, you know it. Okay, you know that what is range? Range is actually set of images of elements of domain. What is the range? Range is the set of images of elements of domain. Great, sir. Understood? Yes, got it. Super. But still, can you explain with the mapping? I'll do that. Let's see. We have the domain here. We have the codomain here. Let's write it again. 1, 2, 3. Here we have A, B, C, D. Let's say A, B, C, D for now. And you start mapping. 1 to A, 3 to D, and 2 to B. That's the mapping done. Okay. Tell me what are the images of the elements of domain? Sir, for the 1 images A, for the 2 images B, for the 3 images D. Yes, you are right. You 100% correct. Then sir, the range will become a set A, B, D. Is it right, sir? Yes, it is right. If you have A, B, D, that is your range because that's your image. What is the codomain here? Sir, codomain you said, na, set B. Set B is A, B, C, D. Right? Set B is A, B, C, D. Not visible. Let me rewrite that. Let me rewrite this. Yeah. Pardon. A, B, C, D is your codomain and A, B, D is your range. Okay, not ABHYAS, A, B, D. The elements A, B, D is your range. Okay, so A, B, D, A, B, C, D is here. The range is here. The codomain is here. Clear, right? What is the difference between range and codomain? That is clear, sir. Sir, come back to on 2. I am just coming back right now. If you see very clearly, are they equal? No, sir. So this has only 3 elements, A, B, D. This has A, B, C also. So A, B, C, D is there. Yes, they are not equal. But if we had an element over here, let's say 4, and you map 4 to C. If you map 4 to C, okay, then the range will change. Then the range will change and you'll have C also over here. You'll have C also over here. Now you check. Is range and codomain equal? Yes. Your range becomes equal to codomain and this type of function is called as onto function. Whenever you can say that range and codomain are equal, the given function becomes onto. Okay, all this represents the same thing. Okay, you can read it, you'll get the notes, you can understand it. Into is what? Just opposite. Even if you have 1 left out, remember the previous case when we had 1 left out? We had 1 left out, right? I had C left out. Even if you have 1 element missing in the codomain which is not having any mapping, I had C left out. Remember, C was not matched with any of the element in the domain. So C was left out. C was filling alone. Whenever you have an element like that in codomain, then that type of function is called as into function. So basically, if your range is not equal to codomain, this is going to be a into function. If it is equal, then onto. Not equal, then into. As simple as that and as easy to understand as that. I hope this is clear. Okay, I hope this is very much clear. Let's have a look. Next we're going to be methods to check whether a function f a to b is onto or into. Method number 1, find the range. Bhaiya, find the range. If range is equal to the codomain, the given function is onto, otherwise into. Next is the long method. You take a value from the you take a value from the codomain. Take a value from the codomain, okay, and that value you put it over here, y equal to fx. Solve for x, find the value of x over here. If the corresponding value of x does not belong to the set A, the domain, if I took a value of y, b is over here. Let's say I took a value of y. I have here a, b, c. I'm taking y equal to c, okay, and there's a mapping over here. Excuse me. There's a mapping over here with set A. Set A has 1, 2, 3, let's say, and y equal to c has no mapping. 1 to a we have, 3 to b we have, but c to 2 is not there. C to 2 is not there. It means y equal to c, if I take and I find the value c equal to f of x and solve for x, it will be an equation, right? You can solve it. Once you solve it, you're getting the value of x which is not present in the domain. Not present in the domain. Okay, then what will happen? Then basically it will mean that so x, value of x does not belong to the set A, then f is not onto and f is into. But if it belongs, means for every value of y belongs to B from the codomain, if you are able to find the corresponding value of x in the domain, it will become onto function. Please check. Okay, basically look through the mapping. None of the elements should be left out. Okay, got it. Methods are clear. Don't worry, I'm going to teach you this while doing the questions as well. Okay, next is bijective function. Simply the combination, if you have 1 1 and onto together, that's called as bijective function. Okay, and it causes the creation of invertible function, but it's not in your syllabus anymore. Invertible function and composite function are not in your syllabus of KCET anymore. Okay, so please understand this very clearly. Invertible function and this is again the related portions came last year. This year we don't have any update so far. So once the update comes, you'll get to know. But right now, invertible function is not in the syllabus, but bijective functions are there. We're going to work on that only. Again, the next concept is going to be number of functions. We have a number of functions given by n power m, where n and m are cardinal number of the set A and B. For A, cardinal number is m, for B it is n. Okay, and number of 1 1 function is given by simply permutation of n p m. Number of onto function is given by a summation of r from 1 to n minus 1 power n minus r, ncr times r power m. Yeah, yes, you have to apply this condition if you want to find the number of onto function. All right, there's again a logic behind this. We'll see that later when we are solving the questions. Okay, I have taken, I think, like that a problem in one of my problem. I think over here all in DPPs, in the PYQs we'll check. Okay, the number of bijective function, this is the true only when you have m and n are equal, otherwise it will be 0. Okay, for bijections m and n has to be equal to 0, so sorry, equal to each other, though your answer will be n factorial. Okay, now we can move on to the problems. We have first one on 1 1 onto function, fr to r, so your domain is all real, codomain is also all real, defined by fx equals to x plus mod of x, then fx is what? Please check, define the function f of x like this. If you take x more than equal to 0, answer will be 2x. If you take x less than 0, answer is going to be x minus x, which is 0, right? So if you draw the graph of this, 2x will be something like this. Okay, and your 0 will be something like this. This is a 0 graph, right? Y equal to 0 is the x-axis. This is the x-axis, and the graph is y equal to 0. This represents y equal to 0. This represents y equal to 2x. You all can see over here, if I draw a line parallel to, or basically on the x-axis, I get infinite number of points. So not 1 1, not 1 1. Correct, na? If you take on the x-axis, I have how many points? I have infinite number of points, right? For x equal to minus 1, minus 2, minus 15, minus 1.5, whatever you take, every time the value of y is 0. Okay, it means not 1 1. And number 2, for onto you check here, what is the range? Your range is what? Your range is all real minus negative real numbers, right? You don't have any negative real numbers over here, only 0 and positive you have. So from all real, remove the negative real number is your range. Okay, so is this equal to the codomain? No, the codomain is all real. The codomain is all real, whereas your range is something is removed from the real number, which is the negative real numbers, so they are not equal. So your range is not equal to codomain, therefore not onto. Not onto. So option D. Option B. Check here. Option D is the correct answer. Next, we can move on now. Let the function f r to r be defined by f equals to 2x plus sin x. X belongs to r, then f is what? 2x plus sin x. Okay. again, for this question we have to use little advanced approach. We're gonna teach you one more time when we learn your derivatives, but right now I'm teaching you here as well. Basically this we learn in AOD, okay, but right now I'm gonna teach you. So to solve this question you have to find derivative. We all know how to find simple derivative, we have learned that. So derivative of 2x is going to be 2, and for this you will have cos x. Derivative of 2x is 2, and for sine it is cos x. Check this out. Cos x is going to be between -1 and 1. Take this value over here. Even if you take the most negative value, which is -1, answer will be still more than 0. It will be 2 minus 1, answer is 1. Okay, so f dash of x is always more than 0, means strictly increasing. So f of x has to be what? Strictly increasing. It means 1 function. Getting it? How come, sir? If the function is always increasing in nature, every time you cut, it'll be having what? Only one intersection, hence 1 function. Okay, let's move on to our next case of onto. So for that we have a trick. Okay, we take the limit of the function actually at 2 points, when x tends to plus infinity and when x tends to negative infinity. Okay, for plus, the answer should be plus infinity. Check this out. If you put here infinity over here, 2 into infinity is how much? Infinity only. And this, if you put anything, it will be between -1 and 1. So this is going to be infinity, and this will be between -1 and 1. So answer will be infinity only, right? So basically when you substitute x with plus infinity, this function also tends to plus infinity. And you should also have the same case in the case of negative infinity. Please check. If you put this back here, limit twice of x plus sine of x, okay, you're gonna get what? Twice of negative infinity plus, again, from -1 to 1. This will also turn out to be negative infinity. Okay, so basically the condition is that x tends to plus infinity, fx also tends to plus infinity. Excuse me. And if you have x tends to minus infinity, fx should also tend to minus infinity. If you have this case true, it means the given function fx is onto. So answer is both 1 and onto, so option A. Both 1 and onto, so option A. Please check. Okay, this is for 1 and that is for onto. For 1 what you're gonna do? Derivative and check for increasing decreasing function, and from there you can check it is 1, and for onto, check for the limit condition. This is the way, the concept. X tends to infinity, plus side, fx should also tend to the same side. X tends to negative infinity, fx should also tend to the negative infinity side. Okay, so next, the last question. The set A has 3 elements and set B has 4 elements. The number of injections. Okay, so injections will be what? Excuse me, injections will be what? 4 P3, right? 4 and 3 we have, yeah. So 4 factorial divided by 4 minus 3 factorial, answer is going to be 4 3 is 12 into 2, 24 by 1, right? 4 factorial is 24 by 1, answer is option C. Correct, now 4 factorial is 24, going to be 4 minus 3 factorial. The denominator is going to be 4 minus 3 factorial, answer is 1 factorial, which is going to be 1, sir. Next, which of the following is 1 1? Of course, this, we all know the graph of this, right? Exponential curve is this only, always 1 1. What about e power x square? If you put if you take f of x as e power x square, right? F of -1 is e power 1 and f of +1 also is e power 1. They are both e power 1, so not possible. Okay, for -1 and 1 not equal, we cannot have f of -1 equal to f of 1. This is a not 1 1 curve, we all know that very well. We'll keep going on like this. We'll have more than 1 intersections if you draw a line parallel. So answer is option A. Okay, so this is the end of your one shot complete revision of your chapter relation and function. I hope you have understood everything that I have explained to you in this. Do join in for your PYQ session and please solve all the DPPs. I have provided the answers as well, but I'm making a request. Do not use the answers before trying from your side first. So try to solve the question from your side first, and later you can use the answer key and answers to rectify if any mistakes you had. If you have doubts, join in the live sessions to ask them as well. Okay, so this is it from the session one shot of your lecture.